In this lecture, we'll talk about why the sun shines so brightly and what we know about the sun's structure. This is an ultraviolet image of the sun taken by NASA's Solar and Heliospheric Observatory. What is going on in there? Why does the sun shine so brightly? Ancient people imagined the sun to be some type of fire. This seems sort of reasonable, but we know that it can't be the case. The question of how the sun shines began to be addressed seriously in the mid-1800s. The idea of the sun being fueled by burning coal or wood was quickly ruled out. Calculations showed that chemical burning could not possibly account for the sun's huge output of energy. By the late 1800s, astronomers came up with the idea that the sun generates energy by slowly contracting in size. Gravitational contraction could have kept the sun shining steadily for up to about 25 million years. And for a while this seemed reasonable, but geologists pointed out a big problem. Rocks and fossils had already shown that Earth was far older than 25 million years. So no, gravitational contraction is not powering the sun. With both chemical processes and gravitational contraction ruled out, what could it be? A completely new type of explanation was needed, and it came with Einstein's publication of his special theory of relativity in 1905. Einstein's theory included his famous discovery of E equals mc squared. This equation shows that mass itself contains an enormous amount of potential energy. The sun's mass actually contains more than enough energy to account for billions of years of sunshine. By the end of the 1930s, it was clear. The sun converts mass into energy through the process of nuclear fusion. Nuclear fusion requires enormous temperatures and densities. How could the sun's core get so hot? Well, about 4.5 billion years ago, a cloud of interstellar gas collapsed and formed the sun. As the cloud collapsed, it got hotter. This continued until the core was finally hot enough to sustain nuclear fusion, because only then did the sun produce enough energy to give it the stability that it has today. The sun continues to shine steadily because it has two kinds of balance that keep its size and energy output stable. The first kind of balance is called gravitational equilibrium. This is the balance between the outward push of internal gas pressure and the inward pull of gravity. The sun's internal pressure balances gravity at every point within, keeping the sun stable in size. Because the weight of the overlying layers is greater, as we look deeper into the sun, the pressure must increase with depth. An analogy is a stack of pillows. The pillow on the bottom has to hold up all the other pillows. The pillows higher up have less weight to support. The same can be said of the molecules in our atmosphere. Pressure is larger at lower altitudes. The second kind of balance is the energy balance between the rate at which fusion produces energy in the core and the rate at which the sun's surface radiates this energy into space. In summary then, why does the sun shine? Well, 4.5 billion years ago, gravitational contraction made the sun hot enough to sustain nuclear fusion in its core. Ever since, the energy released by fusion has maintained gravitational equilibrium and energy balance within the sun, keeping it shining steadily. Our sun was born with enough hydrogen in its core to maintain equilibrium for about 10 billion years. The sun is therefore only about halfway through its 10 billion year lifetime. About 5 billion years from now, when the sun finally uses up its nuclear fuel, gravitational contraction will take over and some very interesting things will happen. We'll talk all about the death of our sun very soon. Let's consider the structure of the sun. The sun is basically a ball of plasma or ionized atoms. The different temperatures and densities at different depths give the sun a layered structure. Let's pretend we have a spaceship that can withstand enormous heat and pressure and that will travel from Earth to the center of the sun. Assuming we have a spectrometer on our spacecraft, we could determine that the sun is made almost entirely of hydrogen and helium. We could also measure its size and learn that the sun is enormous. We could actually fit 109 Earths across its diameter. We would also notice dark spots called sunspots on the sun's surface, and that the sun is not a solid ball. Different parts rotate at different rates. The equator is fastest with a rotation period of about 25 days, and the poles rotate with a period of about 30 days. The sun releases an enormous amount of energy. Only a small fraction of it reaches Earth. Most of it goes into space. Even at large distances from the sun, we can feel slight effects from a stream of charged particles that are continually being blown outward from the sun. This is known as the solar wind. As we approach the sun more closely in our spaceship, we'll encounter the outermost layer of the sun's atmosphere, the corona. It's very hot, about 1 million Kelvin, but not very dense. The temperature drops suddenly as we get nearer to the sun's surface. It's only 10,000 Kelvin in the chromosphere. This is the region that radiates most of the sun's X-ray light. The photosphere is the lowest layer of the atmosphere and is the visible surface of the sun. It's far less dense than Earth's atmosphere and has a temperature of about 5,800 Kelvin. Up until this point in our journey, we would have been able to see the stars if we looked back. But once we go below the photosphere, we are completely engulfed inside the sun. We're in the convection zone, and our spaceship is getting tossed around a lot. There is incredible turbulence here. It's where energy generated in the solar core is transported upward by the rising of hot gas and the falling of cool gas. Below the convection zone is the radiation zone, where energy moves outward primarily in the form of light. The temperature rises to almost 10 million Kelvin. It's calmer here than it was in the convection zone, but our spacecraft is getting hit with some very intense X-rays. Finally, we make it to the solar core, the source of the sun's energy. In the core, nuclear fusion transforms hydrogen into helium. It's very hot, about 15 million Kelvin, and very dense, more than 100 times more dense than water. And the pressure is 200 billion times that on the surface of Earth. It's a crazy and wonderfully interesting place, and I can't wait to tell you all about it. We'll get to the core and nuclear fusion next time.